Welcome to the FMSP revision sessions. We're going to be looking at MEI Markov chains now, and we're going to start off by having a look at some of the specification statements just to make sure you know what you need to know. So the first thing is understand the relationship between random processes, Markov chain models and transition matrices. And you've probably seen in the book that this is all to do with conditional probability. So what we're looking at is the probability of something happened given that something happened the day before. You can do this already using tree diagrams, but the advantage of Markov chains is you can look a long time in the future, and so you can look at what happens on average, what happens in the future, and look for a long time, run lengths, equilibrium probabilities, and we'll talk about those in a minute. We're given some information, and that information to start off with needs to be put into a transition matrix, and that's generally a fairly straightforward idea. But what it is worth mentioning at this point is that you need to be able to use a graphical calculator, because what we involve is finding high powers, and to find the high powers of matrices is something that's not very easy to do by hand. So you need to be able to put these into your calculator, and that generally means you need to put in the size of the matrix, the dimensions of the matrix, and then you need to be able to know how to do powers of this, and that's different for each calculator. What I would suggest you do when you're going through this recording is actually make sure that you do that. When pause the recording and make sure you're putting them in your calculator so that you can use them and check the values that we get. One thing you need to be careful of when you put it in your calculator is just checking whether the value in your calculator truncates or rounds values. So for example, if you've got a matrix with an element 0.1234, it's just checking whether that is actually, it could be 0.12345 and it just stops it at that point, or it could be 0.12335 and it's rounded it. So it's being aware of that. But normally if you hover over that element at the bottom of the screen, it will give you the exact value. And equally, if it's possible to put the values in fractions because you've been working in fractions, again, it may well be that at the bottom of the screen you see the exact fraction. So just being aware of how your calculator works can be pretty useful. We are going to have a practice at a couple of exam questions, and then we'll be looking at using the matrix of transition probabilities. The one thing that you need to be careful of is if it says in 10 days time, well, you need a couple of bits. Firstly, you need to think about what's happening on the first day, and it may be that you're given an initial state for the first day, which could be a vector which tells you the probability of it being in different states on the first day. And the second thing is to think about, well, if it's in 10 days time and we know what happened on the first day, well, that's actually 9 days from the first day. So it may be that you're looking at p to the power 9. But depending on the question, you just got to be careful about whether you look at p to the power 9 or p to the power 10. And again, we'll come across questions like that. In terms of interpreting a given transition matrix, we need to be aware that, say if we've got our 4 positions A, B, C, D, A, B, C, D. In general, what we're looking at is if A happened the day before, what's the probability that B will happen the next day would be this element here. Okay, and as I've said before, we're doing powers because powers tell you what happens in the future. A very simple example, you can check this is exactly the same as you'd get with a tree diagram. It's quite magical, really. To look at future events, as I've just said, that's a case of looking at powers of the matrices. And those will give you the probability of future events combined with the initial state. And obviously it gets a little bit more complicated than that. You might look at the probability that something's happening is going to be the same in 4 days and 8 days, but again we're going to see some examples like that. There's a few different kinds of matrices we may come across. So for our general bog standard matrix, if we keep on doing higher and higher powers, this tends towards a limit. So what that means is if we look at the probability that the weather will be nice today, and then look at the probability that it's nice tomorrow given that it's nice today, well, inject that might depend on what the weather's like today, but if you're looking at 100 days time, the probability that it's going to be nice isn't really going to be affected by what it was like today. So you get this equilibrium matrix with high powers. So we're looking at p to the n as n tends to infinity, or high powers. And generally what we'll get is a matrix where all the columns are the same. And that will give us the equilibrium probabilities. Now, it mentions here specifically non-periodic. There's a couple of other things that can happen. We can have periodic matrices that we'll mention in a little bit, but they're ones where they alternate between different states. We can have ones where you've got p to the n tending to something where n is even, and something different where n is odd. Okay, so it may be for even powers you get one thing happening, and odd powers you get another thing happening, and that tends to be where you've got lots of zeros, alternating zeros and numbers in your matrix, that kind of situation. And then if you're looking at the probability that's in a particular state, rather than just being able to read that off the column, you might have to do an average of two different ones. And that comes on neatly to the equilibrium probabilities, because the equilibrium probabilities are what you find in this limiting transition matrix. And if the columns are all the same, that's very simple. That gives you the equilibrium probabilities. As I said, if you've got two different matrices that p to the n gives you when it's large, so for example, one of them might have a 0, and it's quite common to do that, and one of them might have a 0.5 in it, then the probability there will be 0.25. Okay, you'd work out an average. And again, we'll see some examples of things that are happening a little bit like that. We also then need to be able to calculate expected run length. And this is quite a good one to mention, because you quite often will hear very similar words with the long run probabilities, which are the equilibrium probabilities, and the run length. But the run length means after a particular time, what's the probability that you'll keep on getting that event happening. And this comes from an infinite geometric series. And you'll see it proved in the book, and sometimes in some of the exam questions or examples. But it is perfectly acceptable just to use the formula. The only thing is you've got to be careful, because there are two formulas which you might have seen. If the probability of your event is A, there's A over 1 minus A and 1 over 1 minus A, and you might wonder why one's used in one case and one is used in the other. And if you work them out, it turns out that obviously this one minus this one gives you 1. So 1 over 1 minus A, and that's no coincidence. This is the one that you get for the number of further days. And this is the one that's one more than that, and that gives you the first day included. So if they ask you for the run length and they want the total number of days that it's a particular state, you're going to be using this one. If they ask you for the number of further days, you're going to be using this one. But actually, you can just remember one of the formulae, because they're only a difference of 1 between them. So if you remember that it's A over 1 minus A for the further days, and just add 1 to it, you'll get the total number of days. But just to be aware that you may see different ones and wondering why. Periodic states. We mentioned periodic states before, and this is the case where p to the k equals p for some value of k. It could be of period 2, or it could be of period 3, or other periods, but the most common one is of period 2. So that's when it's alternating between two different states. Be able to work with processes having absorbing states. Well, an absorbing state is where it's impossible to leave. There is a question involving that in one of the exam papers. So it's impossible to leave that state. Once it gets to that state, it stays in that state. So for example, quite a common kind of example is something like, if once you're relegated from the league, you stay relegated. Or if a fly goes along something, if it gets to the spider at one of the ends, it's eaten by the spider and it stays there. The other thing is reflecting barriers. Now the absorbing state will look something like a 1, 0, 0, 0. Remember, because these probabilities need to add up to 1, we always get obviously a sum of 1 in them. So for example, if the absorbing state was A, once it gets to A, an absorbing state being D would look like this. A reflecting barrier looks quite similar. That might be 0, 1, 0, 0. So that means if you reach A, you definitely go to B. It's at a state where the next state is inevitable. So you get 0s and 1s in one of the rows. Okay, so those are all the terms we need to know. I'm going to mention one more thing, which again we are going to test out, and that's to do with the equilibrium probabilities, because it's something that has been asked. Is that if we take our transition matrix P, now the whole thing about the equilibrium probabilities is that that's what's going to happen, what's the probability of what's going to happen in the future. So if we multiply those by our transition matrix, that shouldn't affect those equilibrium probabilities. That'll give us, say, what's going to happen after 100 days. Well, the probability of what's going to happen after 101 days should be the same as what's going to happen after 100 days, or pretty similar. And that's the idea about the equilibrium probabilities. So if you multiply your equilibrium probabilities by the transition matrix, you should come out with the equilibrium probabilities. And that's been used in a few questions recently to go backwards slightly. Rather than working out the equilibrium probabilities, they might give you the equilibrium probabilities and ask you to work something out about the transition matrix. So that's something that's worth knowing about. Okay, so without further ado, I think what's useful to do is to have a look at some exam questions. And we're going to look at June 2010 and June 2011 papers. I've put some of the mark scheme bits on as well, because obviously it's quite a lot of writing out, and we'll try and write out the important bits, the ones that are relevant. So let's have a look at this. So the first thing we need to do is do our transition matrix. We've got quite a lot of information to read, and that's pretty common. An electronic control unit on an aircraft is inspected weekly, replaced if necessary, and is labelled A, B, C or D. So we've got this matrix. They're not going to worry too much about you writing the A, B, C or D down, but it can be useful to do it. In week 1, it's labelled A. So we know in week 1 it's labelled A. And that means if we do want to write an initial state, it would be 1, 0, 0, 0. However, it's quite easy just to read it from the A column. And that's one of the, it's an easier example when you've got an initial state which is just in one unit. When the unit is labelled A, B or C, if it's tested, if it passed the test, it's relabelled B, C or D. If it fails it, then it's replaced by a new unit which is labelled A. When it's labelled D, it's replaced by a new unit which is labelled A. That means that if you start in D, the next thing is going to be that. So D is actually, you get a reflecting barrier there, although it doesn't mention that in this question. I'll just mention it now so that you can remember what that means. So the probability unit fails the test is 0.16. That means if it starts in A and it fails, it goes back to A, that probability is 0.16. With B, it's 0.28. And with C, it's 0.43. Okay. The other alternative for A is that it goes on to B. It can't go to C or D. So that means that probability is 0.84. For B, it could go on to C, so that probability is 0.72. And for C, it could go on to D, so that probability is 0.57. And so that gives us the transition matrix that we're going to be working with. Okay, and I've written that on the next page so that we've got that to refer to. Now this would be a good opportunity to pause the recording if you want to put this into your calculator so that you can use it and check the answers that you get. It's always worth doing that as you go along. So we've got 3 questions here that we need to answer. So for part 2 of this, in week 10, find the probability that the unit is labelled C. Now, we need to remember, although it's week 10, we know what happens in week 1. In week 1, it's definitely labelled A. So we're looking in 9 weeks to the future. So we need to work out p to the power 9. If you use p to the power 10, you would get 1 method mark out of the 3, but that's all you'd get, obviously. To get any further marks, you need to work p to the power 10. And when we work that out, we get this large matrix, p to the power 9, p to the power 9, and the relevant information is that it's labelled C. So we need to look at the third element in here, which works out at 0.2231. Now I will write the other elements in so you can double check them for the first for the first column. I'm not going to write all 16 elements in. You can just double check your answer. And then obviously the other ones. You could have done that by working out p to the 9 times by the initial state, but it's easy enough. It's less to write in your calculator just to look at that first column. And the element that we want is the 0.2231. Okay, and if you remember, it did say put them to 4 decimal places, so just double check that that's not been truncated on your calculator. And so there's 3 marks for that. For part 3, find the week apart from week 1 in which the probabilities that the units labelled A, B, C and D first form a decreasing sequence. Okay, so again, we're going to be looking at that first column because we know we starts in A, but there's no way of doing this except for just trial and error. So you're going to have to work out, just keep on calculating, and what you find is that when you do p to the power 4, the first column of p to the power 4 is 0.5020, 0.2851, 0.1577 and 0.0552, and then all the other bits. But it's the first column that we're interested in because we know it starts with A, or again you could multiply your p to the power 4 by your 1000, your initial state. And the thing to remember is that you'll get 2 of the marks for doing that, but we need to make sure we say which week, find the week, and that's p to the power 4 is in week 5. Okay. And then part 5 is one of those parts that they really like. Find the probability the unit is labelled B in week 8 and C in week 16. So it's a sort of statistics question. It's something and something else. So we need to work out the probability of B in week 8. Well, we can do that fairly straightforwardly. It's week 8, just need to be careful. That's p to the power 7. And if you work out p to the power 7, and the relevant bit that we need to look at is that it's labelled B. So we're just going to look at this element here, which is 0.2869. Again, we've got all the other elements there, but those are the one that we need to know is that it's labelled B. Okay, but then it's labelled P in week 16. And it might be tempting to think, well, that's p to the 15, but actually you've got to remember, we know what happens in week 8. So week 8 is like our starting week. And so week 16 is 8 weeks on from that. So actually what we need to work out is p to the power 8, because it's 8 weeks on from where we're starting. And what we need here is we're starting from not A, but we're starting from B. Okay. We want to know the probability it's labelled C, so we want not the A element, the B element, we want the C element, which is 0.2262. So in fact, the probability that it's labelled B in week 8 and C in 16 is found by multiplying these 2 probabilities together, 0.2869 multiplied by 0.2262, and if you work that out, you get 0.0649. So what's important to notice here is that week 16 is you've got that new starting point, so it's 8 weeks on. And again, that's not an uncommon thing for them to ask. So let's just look at the mark scheme for those 2 parts. As I said, for part 3, you get 2 for finding the power and the column, and 1 extra one for recognising that's week 5 and writing that down. And for part 4, there's 1 for each of those p to the 7 and p to the 8, and then finding those correct elements, 1 for multiplying them and 1 for the answer. Okay, so let's look at the next part of this. Following a week in which the unit is labelled D, find the expected number of consecutive weeks in which it's labelled A. Okay, so we've got an interesting situation here. After it's labelled D, it's definitely labelled A for the next week. And so we want the number of weeks, complete number of weeks. So the way we work that one out, if you want the total number of weeks, we use 1 over 1 minus the probability, and the probability that it's labelled A again is 0.16. And that includes the first week that it was labelled A. If you work that out, you get 1.19. Okay, or they don't also allow 1.2. Obviously, if you are used to using the other formula, 0.16 over 1 minus 0.16, you just need to add the first week in as well, that it's labelled A, and you should get the same answer. Part 6, the equilibrium probabilities. The equilibrium probabilities are found by looking at powers. What you need to be careful of when you're doing this is obviously that when you look at these powers of P, that you actually get ones so that it is tended to, it's got as far as it can go in terms of your 4 decimal places. And there's two checks to this. If it's one where all the columns are going to be the same, then what you can do is look at all the columns. If they're all the same, then you've got those equilibrium probabilities, and this is the case here. So your probabilities are 0.35. If you look at, say, something like p to the power 100, that's normally enough, but I have seen situations where you've had to go a little bit higher than that. So just be careful that in this case the columns are all the same, and if they're not looking like they're going to all be the same, then you might need to go to a higher power if they're sort of quite close. If they're all different, then what you need to check is that if you go p to p to the n plus 1, p to 101, or p to the 200, that you get the same matrix. So just be sort of wary of that. And in this case, I only need to really write out that first column because the other ones are the same, and we can write out the probabilities. The probability that it's A is 0.38, 35, 85, etc. Okay, so there's nothing particularly tricky about that. Now you may have seen methods in the textbook where you're having to find eigenvectors or solve simultaneous equations, but it's quite acceptable, and that's what they're expecting you to do, look at high powers. Okay, now I've put that p to the n up here, so you can double check your results on that, and so we can use that for the next part. And again, this is what I said before, that you need to be careful that we've got run length, we've got long run. Okay, they're using the same word run, but this is in the long run. That's looking at equilibrium probabilities. So how many of these units are expected to be replaced each week? And the way that we can work that out is that we've got 145 of them. Okay, we start with A. How many are we expecting to be replaced each week? Well, that's the probability that you end up with A after a week. So we times by 0.3585. It's that probability. That's the probability that it is replaced. It starts with A at the week in the long run. Okay, and if you work that out, you get about 52 units. Okay, so it's okay to round in this case. It's total number of units. And then we get a slightly different bit, and this is common to the Markov chain questions. At the last section, we'll be doing something slightly different, maybe something slightly unusual that you haven't seen before, or looking at things backwards a bit, or it might have a different matrix that you're working with. In this case, we've got a different manufacturer has now been chosen to make the units. The inspection procedure remains the same, but the probability the unit fails the test have changed. The equilibrium probabilities are now found to be, so in this case they're giving us the equilibrium probabilities, 0.4, 0.25, 0.2 and 0.15. Okay, but we don't know what the transition matrix is, we don't know what those new probabilities are. And that's what we need to find out. And that seems a bit tricky until we remember the fact that actually we know that these equilibrium probabilities shouldn't be changed by the transition matrix because they're equilibrium probabilities. They're a long run. If you keep on multiplying the transition matrix, you should get the same answer. That's the idea of them. So if we know what the transition matrix is, well, that's what we need to find out. We know that it should keep these numbers unchanged. So we should get the 0.4, 0.25, 0.2, and 0.15 here. Now, we know that if it's D, it definitely goes to A, so we know that bit. We don't know what the probability that it fails the test if it's A, but if we call that A, the other possibility is that it goes to 1 minus A. And equally, if we think, well, the probability it does is B, well, we know that that must be a 1 minus b, because obviously probabilities have to add up to 1. And see, this is how we worked it out before, 1 minus c. So this is the matrix that we get. And once we've seen that, it's fairly easy to see that we can get simultaneous equations. So I'm going to ignore the first line because that's got a, b and c, but I'm going to look at the second one that will give us this element. That's 0.4 times 1 minus a. And that gives me 0.25. Okay, and if I do the next line down, that would give me the 0.2, which is this one multiplied by that, I get 0.25 times by 1 minus b is 0.2. And equally 0.15 times by 1 minus c is 0.15. Sorry, 0.2 times by 1 minus c is 0.15. And when you work these out, you get a is 0.375, b is equal to 0.2, and c is equal to 0.25. Okay. So just quickly look at the mark scheme for those, for that last bit, that transition matrix, using the transition matrix, get a method mark for, and using it with, so there's 2 marks for using that, 1 mark for forming the equations and 1 mark for the answer. And actually, it's not the most generous marking because there's quite a lot of concept, but just think if you couldn't do it, at least you don't lose too many marks. Okay. But it's a typical type of thing to happen at the end, that you get something slightly different happening at the end of the question. So that's June 2010. We're going to look at June 2011 now. So again, give the probabilities correct to 4 decimal places. Again, we've got quite a lot of writing, and the first bit is to work out that transition matrix that we're going to be working with for the rest of the question. So let's look at doing that. And they're calling it P, which is quite common. Alpha and Delta are 2 companies which compete for the ownership. Boyles and Cayley is a company which trade. When a new bond becomes available, it's first acquired by either Boyles or Cayley. After a certain amount of trading, it's eventually owned by Alpha or Delta. On the change of ownership takes place overnight, blah, blah, blah. On the first day, the bond is owned by Boyles or Cayley with a probability 0.4, 0.6. So, on the first day, Boyles or Cayley, that gives us our initial state that we're going to be using. So in this case, we're going to need to multiply by that initial state when we're doing these questions. If it's owned by Boyles, on the next day it could be owned by Alpha, Boyles or Cayley with these probabilities. So you've got the 0.07, 0.8, 0.130. And again, if it's owned by Cayley, we've got Boyles, Cayley or Delta, probability 0.15, 0.75, 0.1. And then we've not got the first and the last ones. If it's owned by Alpha or Delta, then no further trading takes place. So it's owned by the same company. And so straight away you can see we've got those absorbing states there, which they're going to ask actually in the next bit. So that's the transition matrix, 2 marks for writing that down. And I've put that up there so that we can use it. Again, it's a good opportunity to put this into your calculator if you need to do that, to do the rest of this question and to check that you can get the same answers, or that you can do it before. Explain what is meant by an absorbing state. Okay, and an absorbing state, it means if a system enters that state, it remains in it. And in this case, it's easy to see that that is A and D. And these absorbing states are A and D. Okay. Part 3, find the probability it's owned by Boyles on the 10th day. And again, like last time, the 10th day, well, we know what's happening on the first day, so the 10th day is 9 days on, so we need to look at P to the 9. But now we just need to be careful because we don't know exactly who it's owned by on the first day. We know it's got a probability of being owned by Boyles or Cayley, B or C, so we need to use that initial state, 0.4, 0.60. And if you do that, obviously because you're multiplying by a vector, you get a vector. If we work that out, we get 0.2236, 0.2505, 0.1998, and 0.3261. So the probability that it's owned by B in this case is 0.2505. Okay, so a couple of marks, multiplying that out and 1 for the answer. Now again, we've got a similar type of question as we had in the last one. Find the probability on the 14th day it's owned by the same company as on the 10th day. The only thing is here, they're not telling us which one they want it to be. So there are actually 4 possibilities. But it can be A and A, B and B, C and C, or D and D. So we need to look at all 4 of those probabilities. And it's the 14th day and the 10th day. Well, we've already looked at the 10th day. That's the p to the power 9. Okay, so that's the bit that we need to look at. And so I'm going to write those out again. P to the power 9 multiplied by 0, 0.4, 0.60. That gave us these probabilities here. And then the 10th day, you need to think about, well, what does that 10th day mean? Does that mean we have to do p to the, sorry, the 14th day? Does that mean we need to do p to the power 13? Well, it doesn't, because like last time, what that means is that we need to look at 4 days on from the 10th day. So we need to look at p to the power 4. Now, rather than write the whole lot of this out, I need to think about which bits are relevant. So we know the probability on the 9th day that it's A, so we need to probably know the probability it's A on the next one, and that gives us a 1. If it's B, I need to look at the probability that it's B on the next one. So it started with B and it's a B, so that's the diagonal element 0.4818. And again with C, I need to know the probability it's C after that. So it's a diagonal element 0.3856, and the D for D because it stays in that absorbing state. So when we work this out, we need to look at the probability that it's A on the first day times by A on the 10th day times by A on the 14th, B on the 10th day and B on the 14th, C on the 10th day and C on the 14th, and D on the 10th day and D on the 14th. Okay, so you multiply these diagonal probabilities, and if I work that out, I get 0.7474. So that's just a slight extension of the question that we had in the last one. For part 5, find the day on which the probability that the bond is owned by alpha or delta exceeds 0.9 for the first time, alpha or delta. So what that means is that we need the 2 probabilities here to add up to more than 0.9. And the only way we can do that is trial and error. So we need to work out P, some powers of P. We need to remember to multiply by that initial state and keep going until we get the first and the last ones in the column are going to be equal to 0.9. So there's quite a lot of work here. But you should be able to whiz through it fairly fast because of your calculator. What you find is that n is 26, we get 0.8971, and that if n is 27, we get 0.9057. So the first time it happens is when n is 27, and again interpreting that, that's on the 28th day. Okay, so the marks for that, again, you need to consider some values of p to the n, and they want you to consider some values bigger than 20, so to appreciate that it's a big value, maybe write down 1 or 2 of the values, but it's enough to consider sort of 26 and 27. Evaluating the probability for some values and identifying 26 or 27 and 1 for the 28th day. Okay. So even if you just wrote down the 27, but it's good form to write down both of them and show that you know that that's the first day on which it happens. Okay, and that's the mark scheme for those 2 questions, so you can see it written out nice and clearly and where the marks come from. Then we've got, again, another standard type thing to ask. The limit of p to the n as 10 tends to infinity. In this case, all the columns aren't the same because you've got these absorbing states, because we know that the probability is that it's going to end up with either A or D. And rather than writing it all out, I've put it on the page for you to check so that it's nice and clear. This is what happens as p to the n as n tends to infinity. So we know that it's going to end up with either A or D. If it starts with A, it definitely ends up with A. If it starts with B, it's got a higher probability of ending up with A. If it starts with C, it's got a higher probability of ending up with D. And that's because of the probability they start with. If you look at the matrix, you should see that that's what you would expect to happen. Okay. Find the probability that the bond is eventually owned by alpha. Now, that's not clear initially, but except we can remember that actually we know the probabilities that it starts with B or C, what they call Boyle's or Cayley. Okay, so if we say, well, that's the long run probability if we don't know who it starts with, but we do know the probabilities where it starts. So if we look at that Q and we multiply it by our initial state, 0, 0.4, 0.60, that will give us quite clearly this vector 0.436100, 0.5639. So what that tells us is that with those probabilities of where it starts, the probability that it'll end up with A is 0.4361. Okay, so given the probability that it's more likely to start with C, then it's more likely to end up with D. Okay, but there's still quite a high chance it'll start with A, and so you still get that reasonably high probability. It's just not as high as the D one. So that's just a case of using that. Okay, so again, a couple of marks for multiplying it out and one for the answer. And then the last bit, again, as I said before, this last bit tends to do something different. So the probability that Boyles and Cales own the bond on the first day are changed, but all the other transition probabilities remain the same. So that means this initial state is changed. Okay, so what's changed in this case is the initial state. We don't know what this initial state is, so if we put P, and there's two things we can put. We could put this as Q, a different probability, or we could just put this as 1 minus P, because we know the probabilities have to add up to 1. And that's our initial state. And then they're saying that it's equally likely to be owned by alpha or delta at the end. So that means that when we did this calculation here, we found the probability of it being owned by alpha was 0.4361. Well, they're saying it's equally likely in this new situation. Now we know the transition ones aren't changed, so our Q should be the same. So this is the equation that we're going to get here. Okay, our Q times by these new initial state probabilities gives us a 0.5% chance of it ending up with either of them, which you might think would be a sort of fair situation. If we multiply this out, we get 0.5738 times P plus 0.3443 times by 1 minus P is equal to 0.5. And when we work that out, we get P is 0.6786. And obviously that's a probability that it starts with C, and the probability that B, the probability it starts with C is 0.3214. Okay, so hopefully that's clear and you can see where that comes from. Again, the mark scheme for that is here. You can see 2 marks for writing that equation down, 1 for the actual equation in P and Q, or 1 minus P, and 2 for the answers. So hopefully that's given you an insight into some of the exam questions and some of the issues that can come up. If you want to find out more about the Further Maths Support Programme, here's where to look, and there will be other online recordings for other sessions on here.